Okay, so welcome to the last class of this course. And in the last class, we might go over time a little bit because I want to cover this, want to say everything I have to say about propagators. So it's kind of a special topic if you want. It won't be covered in the exam, but it is such an important topic that if you stay in physics and even in mathematics, some of these concepts are useful again and again, especially the stuff that I'm going to show towards the end, the contour integral. So yeah, without further ado, let me discuss propagator. Okay. The propagator for the Schrodinger equation. So let's first discuss, what does it have to do with causality? And I have covered this in one form or another before, so this is review, but still. So the thing that I want to make very, very clear is that quantum mechanics is a causal theory. Okay. So what does this mean? It means that if you're given an initial state, say alpha at time t0, then the time evolution operator which we symbolically write as a function of t, and because it has initial condition at t0, it's also a function of t0 formally. So the time evolution operator tells us what's going to happen in the future with absolute certainty. Okay. So it's only when we make an observation of an observable chances come into play. I should not say chances because chance is such a informal word, probabilities, okay? And the way it happens is that we are given a certain probability of a certain outcome, okay? Certain outcome. But as long as we are not doing that, the time evolution operator is, predicts the future with absolute certainty. Okay? So the time evolution operator, which I'm also going to call the propagator interchangeably, is a unitary operator, right? What is the meaning of this, of its unitarity? What it means is that probabilities, in quantum mechanics, probabilities come one step after what is interesting. What's the basic objects are called transition amplitude. Transition amplitude. And what is a transition amplitude? Suppose we have a state alpha at t0, another state, say beta, t0, then the inner product is telling me what is the amplitude that the state of the system will transition from alpha to beta. And then squaring that gives us the probability of the transition. So What we call the probability, the normalization of a state is a special case of this transition amplitude when beta is equals to alpha, right? So the transition amplitude, they contain all the physical information. And the unitarity of the time evolution operator or the propagator tells us that, none of the information contained in the transition amplitude are lost. For example, if I take the transition amplitude of the state beta at time t from the state alpha at time t, then the time evolution operator is telling me that it's related to the state alpha at time t0 via u, and the beta at time t is related to the beta at time t0 via u dagger. But u dagger u, because of unitarity, is 1, and therefore this is the same thing as beta t0 alpha t0, okay? So unitarity is about preservation of information. You can say of quantum information. Any information that is contained in quantum states is quantum information, okay? It doesn't have, we don't have to discuss information theory to understand what quantum information is. Quantum information, you can say, is all these objects. Okay, is it clear why unitarity is so important for preserving causality? Because if you lose information, then your theory is no longer causal. If you lose information, then you would not be able to predict the future. So quantum theory is a perfectly causal theory, okay?